series is going to be n equals 1 to infinity, 1 over n squared. So this is something that we haven't looked at before. It's not geometric, it's not telescoping, it's not the harmonic series because my power is 2. So right now, I have no idea if this converges or diverges. And we can't really find a formula for S sub n. So instead what I'm going to do is I'm going to start looking at looking at the partial sums. Okay? So n and S sub n. So if I add up the first 5 terms and you use a calculator to add that up, you're going to get 1.4636. Okay? And we want to see what happens as n gets larger. So in order to do this, we're going to need most likely a computer to help us add these up. The first 10 terms, 15498. The first 50, 1.6251. The first 100 terms, 1.6350. And the first 500 numbers, if you add them up, you'll get 1.6429. Okay. So remember, I have this series. I look at its partial sums, which is this list here. We've kind of looked at partial sums now. So what's your feeling? Do you think that the partial sums converge or diverge? Look at that list of numbers. I think that maybe it converges because the numbers are kind of staying close to each other, right? 1.62, 1.63, 1.64. And I'm adding, that last one I've added up 500 numbers. That's an awful lot, right? So the feeling is, it looks like the partial sums converge to a number near 1.64. And remember, if your partial sums converge, that tells you that your series diverges. Okay? So again, it looks like your series 1 over n squared converges. I keep saying it looks like because this isn't very precise. This is just our initial feeling, our initial guess. Okay? So what we're going to try to do is make this more concrete. So what I'm going to do, I have my series that I'm interested in, 1 over n squared. I'm going to turn this into a function. Okay? So I'm going to replace n by x, 1 over x squared. And now let's graph this function. I'm only going to graph part of it, not the whole thing, because we're only interested in positive values of x. Okay. So if I plug in 1, I get 1. If I plug in 2, I get 1/4. 3, you're going to get 1/9, and so forth. Okay. So I have this curve, and then what I can do is I can take Riemann sums. I'm going to take right-hand Riemann sums here. So let me do that. Okay, and then if I'm doing a Riemann sum, I want to know the area of these. Okay, so we're doing a right-hand Riemann sum. And let's add up, let's calculate the sum of these areas of these rectangles. So what's the width of each one of my rectangles? 1. And then the height comes from my function, right, where I plug in my right endpoint. So the first one, it's 1. The second one, I plugged in 2 into my function, 1 over 2 squared, 1 over 3 squared, and so forth. All right, but this is really, so this is the area of my rectangles. But this is also my series that I was interested in. And remember that the Riemann sum, what it does is it approximates the area under the curve, right? So, but we know how to find the area underneath that curve. We're going to look from 1 to infinity of 1 over x squared. And let's see if that integral converges. So do you remember how we calculate these improper integrals? What's our first step? Put in a limit, right? So I'm going to put in a limit, get rid of that infinity. And what's the integral of 1 over x squared? Negative 1 over x, 1 to t. And then plug in your bounds and compute that limit. So plug in t, negative 1 over t, and plug in 1, so it's minus a negative 1, so plus 1. And what's that limit going to be? 1. So what did I just do? Let's look back up at our picture for a minute. I calculated the area from 1 to infinity. So the first thing to notice is I left out my first rectangle, right? That first rectangle from 0 to 1 wasn't included. So let me take that rectangle, which was the area of the first rectangle was 1, and add to it this area that I just calculated, which was 1 plus 1, or 2. So what I did is I added up, let me go back up real fast to the picture. I added the first rectangle, and then I added the area under the curve from 1 to infinity. But I've calculated too much area, right? Because what I've done is I've included this area. I've included area that's outside of my rectangles, right? So I overestimated the area of my rectangles, right? So this 2, it's an overestimate of the area of my rectangles. Well, an overestimate is also known as an upper bound, right? So what we've just said is that the partial sums are less than or less than 2. I'll just say less than 2. So this tells me as a sequence, they're bounded. They're bounded above by 2, and I'm adding up positive numbers, so I have a lower bound of 0. Also, if I look at the partial sums, they're going to be increasing. And that's because every time when I go from S1 to S2, S2 to S3, I'm adding another positive number in, which means my sum is getting bigger, right? Because terms are positive. Well, if you're increasing, remember that means you're monotonic. So look at the two words that I've just underlined. I have a sequence that's bounded and monotonic. Don't we know something? Every bounded monotonic sequence converges. It's that monotonic sequence theorem we talked about before. So the monotonic sequence theorem tells me that the partial sums S sub n converges. If your partial sums converge, what happens to your series? Does it converge or diverge? Partial sums converge, so your series also converges. Okay? That's how we defined it. So this tells me that 1 over n squared also converges. Any questions on that? So again, the idea is I want to calculate this Riemann sum because this Riemann sum represents my series. I can't explicitly compute that, so instead I approximate it by computing the improper integral. It's kind of the opposite of what Riemann sums usually do. Usually you use a Riemann sum to approximate an area, but now we're using area to approximate a Riemann sum, so it's a little backwards. Okay? All right.
So how did you know to add the 1 on that?
So the problem was, if I look at this integral from 1 to infinity here, what I've done is I've calculated these areas of these rectangles plus the blue area, but I left off that first rectangle.
Okay.
So that's why I needed to add it back in. It's because I didn't include that other rectangle.
And how do you know it's 1?
So I integrate from 1 to infinity. If you tried to integrate from 0 to infinity, it would be an improper integral for 2 reasons, the
Because
infinity
of the
and the 0.
Okay.
So instead I do it from 1 to infinity.